Hey everyone, how you doing? I wanted to make a quick recording showing you how to do this population growth activity and how to use your Desmos calculator to get some good graphs and to come up with some functions that seem to fit the data. So we've got this data here from Oregon, New York, and the United States as a whole. For the last 60 years, you can see from 1950 to 2010, Oregon has definitely been growing in terms of population. Doubled, over doubled in that time span. But what we want to do is be able to take a mathematical model and see if we can come up with an equation that shows, well, how fast are we growing? How much might we grow in the future? So that's what we're going to do. We're going to use this data. You're going to use New York, US, as well as Oregon, but we're going to work to Oregon together to get some good start here. All right, I've opened up my Desmos calculator, and I've already went ahead and put in the data for Oregon. Again, you'll just want to add an item, add a table, and then when you add in the table, then you can come in here and just fill in, click on it, and type in the values that you want to type in. So we got all the data in there. That'll take a little bit of time to get it set up, and you notice nothing shows up. Where are my points? Well, we've got our standard graph here that goes from -10 to 10 for x and from -6 to 6 for y. But when I look at these numbers, I'm dealing with thousands of numbers, 1950 to 2010 for x, and I'm dealing with 1,521,000 all the way up to 3,831,000. So I need to adjust my window to be able to see these things. So let's go to graph settings. And here I can adjust the x-axis, where do I want to see, and I can adjust the y-axis, where do I want to see. So I'm going to make it so I can see these points. So let's click on x-axis. Instead of starting at -10, I'm going to do 1940. I'm going to go 10 years past 1950 earlier there. That'll include that point. And I'm going to go all the way up to 2020. So I like to get a little bit of a buffer, go past beyond the points that I have. And we'll make a step every 10 years that will make a line. There, we've just dealt with the x-axis. You can see my graph is adjusting already. Now for the y-axis, let's start at 1 million. 1, 2, 3. 1, 2, 3. And let's go up to 4 million. That's a good window to be able to see. 1, 2, 3. 1, 2, 3. And we'll make our steps at, let's do 250,000. All right, there is my graph. Now I can see all the points, right? This is the Oregon growth data. And you may want these points on, you may want them off. I'm going to leave them off because they're kind of big and they cover up a lot of stuff. But we got the points. I can zoom out a little bit more if I want to zoom out a little bit more. And I can adjust it. Maybe there's too many lines. I can go back to my graph and I can change the steps. Instead of going up by every 250,000, I could say let's go up every by 500,000. And that looks a little bit cleaner now. Okay, the other thing I might want to do is I'm trying to see how well these curve. Let's adjust instead of points. Let's go to the settings. Click on this. Instead of just dots, let's make it dots, but we'll connect the lines as well too. And, well, green's good. We'll leave it at green. Okay, now I've got a good graph of my data. I can see it's growing. Now the question is, what kind of function? Do I want a linear function? Does it seem like it fits a straight line? Or do I want a curved one? We have exponential curves we could use, or we could have quadratic equations that we could use. And I'll show you how to do all three of those and how to test which one actually seems to fit well. There we go, our data's on there. Now we're good to go. So a linear function, let's start with a line first. A linear function is y equals mx plus b. All linear functions can fit in that form. So let's test how well this fits in a linear function. Here's my y. I want to pull in data from y1. So I'm going to do y1 is equal to, but I'm not going to use the equal sign because I'm coming up with an approximate line of fit. So I'm going to pull up this little keyboard. I'm going to use this little, where is that little tilde thing at? Let's go to functions. stats. I'm going to use this little symbol right here. I don't know really what it's called, but it's squiggly line, and it means approximately. So now I've got y1, my y values, are approximately equal to m, my slope, times the x values, mx plus 1, plus b. So I'm doing the general form of a linear equation. And look what happens. I'm going to change the color on this because I don't like double green. Let's make this one blue. But there you go. I've got a line of fit that seems to run right through all my data points, don't I? I like it. So this is a line I can fit points. Some are a little above it and some are a little below it. But if you compare it to the green line, it seems to fit reasonably well. Right? It seems to look like it follows along. And what this would say is for Oregon, this would be a nice linear growth. Every year it grows by the same amount, roughly by the same amount. Over the last 60 years, it's historically grown by a nice, steady, linear amount. What do all these things mean? This would be my slope, m, and that would mean every year we grow by 39,232 people. B, my y-intercept, this is kind of a weird number. It means in the year 0, if I go all the way back to 0, this is my y-intercept, there was negative 75 million people. That doesn't really make sense other than we have a model and that's just a linear model and how it fits. So kind of, you can't take this thing too extreme. It works really good within our data here. What I really want to get into is this r squared value and this r. This tells you how well our data fits. So when we have r equals 0.994, that's telling you, wow, our data fits really, really well in a positive direction. If it was exactly 1, that would mean all of our points fit exactly on a line. If it was negative 1, it would mean all our points, it's a decreasing graph, but it fits perfectly. If it was 0, exactly 0, it would mean there would be no correlation. This does not fit a line. It does not fit anything. So we got 0.994. That was really high. That means that this linear equation is a good fit. And so I could say, all right, well, y equals, there's my slope m. I can put that in for m. There's my y-intercept b. I now have a function, a linear function that fits our data. But let's try some other ones. It does look like it could be a little curved. So let's delete that one. Let's try a quadratic graph. So quadratics are y equals ax squared plus bx plus c, right? This is the general form of a quadratic equation. So let's do that same thing here. Let's go y1 is approximately equal to a times x1 squared plus b times x1 plus c. Now we've got a general form for quadratic, and we're going to see how well this thing fits. Well, if you look, there's my parabola, right? It's definitely curved, and this thing looks like it fits pretty darn good as well too, huh? I like it. It's interesting. Well, what can we tell from that? I don't have an r, but I have an r squared is 0.994. That's telling me this thing fits pretty good as well too. And it's giving me the value for A, the value for B, and the value for C in my quadratic equation. So now I have a quadratic equation that fits my data. Which one fits better? Well, this r squared was 0.994. Let's go back to do the linear one and see what the r squared value was. This r squared is 0.988. The other one was 0.944. Well, 0.988 fits a little bit better than 0.944. So I'm going to say the linear function seems to be a better fit statistically than my quadratic one. All right, the other only one to test would be an exponential. So that is the form y1 equals some starting value, a, times b to the x1 power. So now we're relating. Whoops, I can't do equals. I got to do an approximately equals. There we go. So now we're relating x1 and y1, these two variables, but in an exponential form. Wow, look at that. This one does not seem to fit very well at all, does it? We could add a constant, but that makes it worse. So what I'm gathering is an exponential function. Definitely does not work right here. You can see from the r squared it's 0.9. This is reasonable, but it's 0.906. That's not as good as the 0.99 or 0.94 that we had on some of the other ones. But we can get a graph, we can play around with some values, and it's just not growing the same way. All right, hopefully that's a good introduction to using the Desmos calculator and working with data and coming up with functions that fit our data.